In this video, we will look at EMF and internal resistance. Now, previously, we would have examined the relationship between EMF and PD, so we'll do a quick review of that before we look at EMF and internal resistance. Now, electrical components basically convert energy from one form into another. There are certain devices called passive devices like lamps, wires, resistors, switches, and so on, which basically convert electrical energy to other forms of energy. So these devices, they do not supply electrical energy to the circuit, but they actually convert electrical energy to other forms, right? Whereas there are devices, we call them sources, which actually supply electrical energy to a circuit, and these devices convert other forms of energy, could be mechanical, chemical, and so on, to electrical energy. And we speak about PD and EMF in relation to these energy conversions, right? So we speak about the potential difference or the PD across passive components like lamps, resistors, and so on, based on the conversion of electrical energy to other forms. And we speak about the EMF of sources based on the conversion of other forms of energy to electrical energy, of course, when charge flows through these devices, right? So looking at the sources and EMF, basically, if a certain amount of energy, say W, is converted from other forms to electrical energy, when a quantity Q of charge flows through those devices, then the EMF E of the device is given as W over Q. Right? So the EMF of the device basically is a measure of how much energy is converted from other forms of energy to electrical energy per coulomb of charge which flows through the device. So for instance, if say 10 joules of energy is converted when 2 coulombs of charge, converted from other forms to electrical energy, when 2 coulombs of charge actually flows through the device, then the EMF of this device would be equal to 5 volts, right? So let's say we have a battery of EMF 5 volts. So we have a battery of EMF 5 volts. Now, ideally, the EMF of this battery should be constant regardless of what magnitude of current it is actually driving to an external circuit. Right? So ideally, the EMF should be constant. But generally, this is not the case. Right? If we have a battery in a circuit, for instance, that is driving a current through a device, say a resistor. So if this is, say, a 5-volt battery, and it is driving a current through a resistor or a lamp, then essentially if we take a voltmeter and we connect a voltmeter across the battery, it will not give 5 volts, right? It will give a value which is less than 5 volts, right? If we increase the number of resistors, let us say connect them in parallel, then this will actually increase the current which is actually being pulled by the circuit from the battery, and the reading of the voltmeter connected across the battery will even decrease further, right? So basically what this shows is that whenever a battery is a part of an external circuit and is driving a current, if we take even an ideal voltmeter and connect it across the battery, it does not read what is supposed to be the true EMF of the battery, right? Now, why is this? The reason for this is that batteries, they have what is called internal resistance. Now, batteries, as well as other sources, are made from the, materials which have a certain amount of resistance. And the resistance of these materials basically provide the internal resistance of the battery. So basically what this means is that whenever a battery is actually driving a current around an external circuit, then when that current basically returns to the battery, there is some energy dissipated within the battery due to the combination of the internal resistance and the current flowing through the battery. And so, as a result, when we connect a voltmeter across a battery, it does not give the true EMF of the battery. And that reduction in the EMF is referred to as the lost volts, right? So, if we have battery, let's say the EMF is supposed to be 5 volts. Now, we know that batteries have internal resistance, and to indicate that, we'll include a small resistor in series of the battery. So this represents the battery's internal resistance, but this, of course, entire thing is the battery, right? If we connect an ideal voltmeter across this battery, now let's say this is a 5 volt battery. If this is an ideal voltmeter, it basically means that it will have infinite resistance in theory, or in practice, very high resistance, and will therefore draw no current from the battery. So because it is drawing no current from the battery, then we have no energy being dissipated, and so the reading is, of course, gives the EMF, which of course is 5 volts, right? Now, however, when we connect this battery to an external circuit, let's say a lamp or a resistor, and we take the measurement, it will not read 5 volts. So if we connect this to, say, a resistor of resistance R, so that the battery is now driving a current I, and we connect the same ideal voltmeter across the battery, the reading that we get, let's call it V, would be less than the true EMF of the battery, right? And this is due to the fact that some energy will be dissipated within the battery due to its internal resistance, and that reduction in the battery's EMF is referred to as the lost volts, right? Now, we can look at a relationship between this EMF, the lost volts, and of course the PD across the battery. Now, we know that basically energy is always conserved during processes, right? So this basically means that if there's a certain amount of energy being supplied, then the same amount of energy will always be. However, that energy may be converted from one form into another, right? So basically, the battery is supplying electrical energy, and of course, the resistor is using up some amount of that energy, and of course, some amount of energy is also dissipated within the internal resistance of the battery, right? And if you recall, we defined EMF and PD in terms of energy changes per coulomb of charge flowing. So basically, applying that principle, we can say that the battery's EMF E is equal to the terminal PD across the battery, let's call it VT, plus what we call the lost volts, right? So the EMF of the battery E is equal to the terminal PD plus the lost volts. And this terminal PD, of course, will be the same as the potential difference across the resistor R, right? But of course, you know that E or V is equal to IR. So we can write that the EMF E is equal to I times the total resistance R, and not total resistance, but the circuit resistance R, and this is the plus I times the internal resistance small r. And so basically we have E is equal to I times R plus R. So this equation basically shows the relationship between the battery's EMF E, the current being driven by the battery, the external circuit resistance R, and the battery's internal resistance small r.